My guest today is Professor Thomas Maschmeyer, who's Professor of Chemistry at the University of Sydney. He also serves as the founding director of the Laboratory of Advanced Catalysis for Sustainability, and is also an executive chairman of the Gelion Technologies. I hope I pronounced this correctly.
Close enough.
Close enough. So there are a few topics we want to talk about. And I want to start with the batteries, Thomas, because I'm very, very interested in that. So Gelion is a battery company, isn't it?
Yes, that's right. So just for the record, it's Gelion, but close enough.
Okay.
Gelion, that's close enough. Yes, yes, it's a battery company, and we are one of the main companies around the world that pursue lithium sulfur technology as the next generation for ultra high energy density batteries on the gravimetric scale. So basically, a very light battery compared to what is around now.
Yeah, even though I was an engineer, Thomas, I have very little understanding of batteries. So you said lithium sulfur. So most of the batteries in the electric car arena now is lithium ion batteries, right?
That's right.
So
Yeah.
how is this different from that?
Yes, so we still use lithium, but we use lithium in a form that is either an alloy with silicon, and we are there working together with a US company, Iron Blocks, who have an anode. So a battery has an anode and a cathode, the plus and the minus. So that is a lithium silicon alloy, so it's a metal. And the other version is to use a protected version of lithium metal as the anode. So it's not an ion as such. However, when the battery discharges, the metal releases the lithium ion, and that is traveling across the battery. And on the other side, we have sulfur, which is extremely cheap, very light, and replaces the conventional cathodes, which are currently in your iPhone, nickel, manganese, cobalt oxide. So it's a very complex, expensive, and with the cobalt in it, toxic and also questionable in terms of how the cobalt is generated, from mines in the not very democratic Republic of Congo under really bad conditions by child labor and all the rest of it. So cobalt has a bit of a problem with it. So we are replacing that and making it lighter and safer.
So I want to get to understand the mechanics of this a little bit more,
Yes.
Thomas. So there's an anode and there's a cathode, and there's some stuff in between that.
That's
right?
it. Yeah. Okay. So that's electrolyte. Yeah.
So that's a battery, and we have had a lot of I shouldn't say problems, but a lot of complications around when the stuff in between those is pure liquid. It has some complications, right? So over time, it reduces the effectiveness of the battery. So what's the mechanism that does that?
Okay. Yeah. So good question. So batteries in general have many different what's called failure modes. So anything and everything can fail in a battery: the cathode, the anode, the electrolyte, the membrane, the connectors, you name it. It can go wrong. So that's why batteries are quite difficult, although they're in a sense simple, right? It's just a little sandwich package. Anything that can go wrong. The issue is it needs to keep doing the same job over and over and over and over again without changing whatsoever. That's the tricky part. So lithium sulfur, just to take a few steps back. So the lightest metal that we can use is lithium, and the lightest element on the other side we can use is oxygen. And so the lightest battery you could possibly make is lithium and oxygen. But as you will know, oxygen is a gas. So that is difficult to put into a battery, and there are ways of doing it with gas diffusion electrodes, etc. But then you need to put things in addition to the lithium and the oxygen into the battery, and you're starting to lose your weight advantage. Sulfur, if you look at the periodic table, is below oxygen. So in a sense, it's like solid oxygen. So it's the next closest thing. and that's where the weight advantage comes from. So what
So
happens? Yeah,
yeah.
yeah,
So sorry to interrupt. So all the batteries that I have seen, Thomas, there's lithium in there, one way or the
mhm,
other. Why is lithium so attractive for batteries?
right. Lithium is the lightest metal, so that just makes it very attractive. But there are now sodium batteries coming on the market. Sodium is larger, is cheaper, it's heavier. Um, its diffusion is not as fast because it's bigger,
Hmm.
and one needs slightly different approaches. So the sodium requires something called hard carbon rather than graphite. So the lithium is able to what's called intercalate, so sit in between the layers of graphite. So graphite are just very thin layers, like a stack of cards of carbon stuck on top of each other.
Yeah.
And then in between the cards, in between these layers, the lithium can go in and out. And you can never get all of the lithium out because then the stack of cards will collapse and there are no gaps anymore.
Hmm.
So that's when you overly discharge your battery, it dies. So that's why you always have to have 20% charge left in a lithium ion battery.
Hmm.
And sodium ion it needs a different approach where you have islands of this graphite but stabilized by different form of carbon, and that together is called hard carbon. And people said, well, this is too hard to actually manufacture at scale, but there have been a number of breakthroughs over the last few years, and there are a couple of companies out there now showing that it's possible. But it is heavier, it's slower, and it's really something for stationary energy storage.
So sodium is plenty available.
That's right.
Lithium, not necessarily so,
Yeah.
I would imagine. And so sodium ion, if we can do that, that would be very attractive, right?
Yeah, it's very attractive. The battery designs that are out there now, there is, for example, one company in the US called Unigrid. They have a tin sodium alloy, a little bit like the silicon with lithium. They have a tin sodium, and that can be paired with a number of cathodes, including
Hmm.
sulfur. And so you know, I guess theoretically speaking, the cheapest battery that could be out there is a sodium sulfur battery that works at room temperature. There are sodium sulfur batteries out there that work in the liquid state, so about I think it's 350 degrees or so, but that has its own engineering challenges. So that is an active field of academic research.
So your company, so what's the technology of the gel that you have in between those cathode and anode? Yeah.
Right. That is so when an ion is moving from one side to the other, there is a charge that is moving. And I can't just have that move on its own. It needs to be supported by some other charges so that overall the charge is neutral inside the battery. So you
Yeah.
need something called a supporting electrolyte. And our bodies are the same, right? I mean, when we get a cramp, for example, then our electrolyte balance is not quite there, because those similar, phenomena inside our nerve cells are slightly off. So these electrolytes are very important, and the gel is a version of a semi-solid electrolyte, which has got some advantages because
Semi-solid. So
it cannot evaporate so easily, for
yeah.
example, or at all, depending on what it is. And from a processing point of view, it can be made into a film. There are a number of advantages around
Hmm.
the gel.
So I have no understanding of this, Thomas. So I'm just asking. So there is some sort of a membrane in between. If it was a liquid electrolyte, you need
Yeah.
some sort of separation, right, for it to work?
That's right. Yeah. So you need electrical separation between the anode and the cathode. So that's one function of the membrane, and the other one is to select the ion transport. So we get electrical neutrality, but we also are allowing ions to flow in the way that we wish.
Do you still need that in the gel? that you have in your batteries?
So the gel can have more than one function. And so the gel can be the electrolyte as well as have a membrane type function. That's right.
Oh, wow, okay. So yeah, so we went from sort of liquid electrolytes to there were a lot of talk about solid electrolyte batteries. But yours is sort of sitting in between those two things, right? In
That's
some
right.
ways. Yeah.
So yeah, so currently in terms of approaches to lithium sulfur batteries, there are companies that are pursuing a similar design to what is in your, the liquid, the lithium NMC battery, like what's in your smartphone,
Yeah.
and that is a reasonably high level of liquid electrolyte in there. And then there's another extreme where one just uses a solid state electrolyte, and there are issues with either of those extremes. The first issue with the liquid one is a liquid electrolyte. It just takes space and weight. It doesn't actually store any energy. It's just a medium that allows the battery to function. So if I
Is
have
it
a lot
also
of
inflammable? Is that one of the
yes,
issues?
it can. Yeah, it can. That's right. Once the battery starts to burn, that's also one of the things that can burn. So it just occupies space and weight. So your
Yeah.
energy density is by definition not as high as it could be. On the solid state electrolyte, think about two different sheets of paper or plastic or whatever, and you put them together electrically and ionically in terms of ions moving. They have to have perfect contact for there to be the lowest possible resistance. On the
Yeah.
atomic level, there's not going to be perfect contact. There's going to be gaps. If I have a liquid, well, that'll sit in the gaps and there will be a perfect contact. But if I don't have anything, I need another strategy, and that strategy tends to be pressure. So one puts a lot of pressure, so it sort of melds together, right, up to a point. And that has its own engineering challenges and introduces its own issues in terms of having extra things in there for weight and for volume, right? Because you need to apply the pressure in some manner. So what we've done is we are using a very small amount of electrolyte, liquid electrolyte on the sulfur side to make sure we have this really good connection. But it is so little that the sulfur itself, when it becomes charged and turns into what's called a polysulfide, and it peels off the solid sulfur and is mobile, it actually doesn't do that. It has the conversion entirely happening in the solid state. And we talked before about battery deactivation, the polysulfides moving across through the membrane, through to the other side of the battery and reacting with the lithium. That is how the lithium battery can deactivate. So we are basically using a solid state conversion on the sulfur side, but we still have a good contact because we have a tiny little bit of electrolyte in there. So it's the best of both worlds. And we had some of our own IP, and Johnson Matthey, one of the very large precious metal companies that makes catalysts, or makes about a third of the world's car catalysts. It makes a lot of catalysts for the petrochemical industry, makes electrolyzers or whatever. They made a strategic decision to get out of batteries, and we picked up the relevant patents for us, relevant from them a few years ago, and now we have about 80 patent families in this area, and that in between space is that the space that we occupy. And if you look at the academic literature, I think it's pretty clear that that is a very attractive space.
So can you describe the cathode and anode in your battery?
Yeah.
How are they? What are the materials there?
Well, so we have a current collector, which is the same as when you have a normal battery, and there are different types of metal foils. I won't tell exactly what they are, but I mean, just for other batteries, you have a copper foil or aluminum foil or whatever, and then you coat onto that foil your electrode active material, which for a lithium ion battery will be a mix of graphite and lithium ions. Well, initially just graphite, and then and then on the cathode, it would be a mixture of carbons and this nickel manganese oxide, cobalt oxide material, and they sit on these thin sheets of metal foil, and then that's wound together or put together as a folded as a stack. So in your phone, it's a stacked battery. It's a pouch cell, as is known, and you can have the same concept in a wound cell in a AA battery size or bigger for electric cars.
Yeah, I mean, this is a fantastic material science challenge. In
Yeah.
many ways.
So one of the big issues with lithium ion batteries is that the two current collectors, the two foils, are two different metals, and if they come in contact because of bad manufacturing, there's an electrochemical reaction that happens spontaneously. So it's a chemical reaction, really, and that can create a local hotspot. And
dangerous, right?
that is one of the key elements of why we get battery fires. And the second version of that is if everything is manufactured well, but there's a physical deformation because of an impact of sorts. And that's why when your phone drops in the airplane seat, they say, don't touch your seat, don't move backwards, because it can deform. And then these foils can come into contact, create over time a hotspot. The hotspot will start to ignite some of the materials in there, and then off you go. Yeah. So the nickel
this is what they call the dendrites. So over time, you have some growth on.
Yeah. So different batteries have different issues. So one of the advantages of a lithium ion battery is that there's not really much of a dendrite issue, because you're just moving the lithium ion from in between the the graphite plates. It goes in and out. So one of the big breakthroughs for lithium ion technology was to avoid dendrites by definition, because you don't have the lithium in there. If it's poorly manufactured, you can still get dendrites. But for the alloying or the metal plating batteries, as we are, for example, introducing, and some other companies are, there are dendrite issues, and then they can be mitigated by a range of different approaches.
So you mentioned sulfur, you mentioned sodium. So in your battery, what are the major components of your battery?
Oh, so in the we have lithium metal, or a lithium tin on the anode, and we have sulfur on the cathode, and the sulfur in itself is non-conducting, which is of course not great if you have a battery. So it needs to be dispersed in a conducting matrix, and carbon plays a big role there. And then we have our electrolyte that is able to match our sulfur cathode, which is where our main intellectual property lies, to a range of different anodes. So we can match to a lithium lithium graphite ion anode, lithium ion anode, just the normal anode. We can match to lithium metal. We can match to lithium silicon. We can match to whatever's out there, by adjusting that tiny smidgen of electrolyte to then make the chemistry work between the two electrodes.
So what's the composition of the gel itself, the electrolyte?
Well, that's our IP, so I can't.
So you cannot talk too much about it. Okay.
Yes.
Yeah. So, I mean, it seems like there are three parameters. One is, so thinking about electric vehicles. One is range. How much energy could be stored in there. One is cycling. How many times can you recharge it? So what are the Well, there must be a third one. I can't remember what it was, Thomas. But
energy density is and volume, of course, of the battery.
Sort of the
safety.
weight issue,
Safety
right?
is a big one, right? I mean, does it blow up or not? So in our case, it doesn't blow up, because if the lithium ever were to do something untoward, because it is so close to the sulfur, the first thing it will react with is the sulfur. and lithium sulfide is, a very inactive material. It's like rust except with lithium.
Hmm.
So it doesn't do anything. So the battery will self-deactivate. So it's very safe from that perspective. And range is a big issue, of course. And so in our case, because we're about half the weight, or if you compare it to lithium iron phosphate batteries, about 2.5 times more energy density by weight. That
Yeah.
means for the same weight of battery, I can drive 2.5 times the distance, or I can choose to drive a shorter distance with a lighter battery, which then actually becomes a self-reinforcing story because the car itself becomes lighter. So I need less energy to move it. So you're actually gaining as you go down significantly as well. And the car becomes cheaper because it is lighter. The brakes, which have to be re-engineered for electric cars, and the tires and everything else can stay the same as in conventional cars.
So on the weight issue, is your battery lighter than lithium ion, the sort of the status quo?
Yes, yes. We currently published that we are about 400 watt hours per kilogram, and the best lithium ion batteries out there now, I think, are about 240 watt hours per kilogram. So we're almost double. And compared to lithium iron phosphate, they're about 160 watt hours per kilogram. So we are more than double the energy density.
So this seems like a much superior technology. Why aren't the electric vehicle manufacturers have all gone in
Yeah.
this direction?
Um, First up, if you have any new battery technology, no matter what it is, ours, and it's fully certified, and people say this is the way to go, and I have independent verification from Sandia National Labs and around the world, and fulfill all the standards. The car industry says then it will take us 6 years before
Hmm.
you will find a car with that battery in the showrooms. So there's a big lag. So the car market is a really conservative one to break
Hmm.
into. That's one of the reasons. But Stellantis, for example, has just announced with one of our competitors a big initiative of lithium sulfur for cars. So
Hmm.
it's certainly coming. And yeah, the material science, the understanding of the carbons is quite critical, and there have been a lot of advantages made. And really, I guess there is now a driver by the market to say, well, the batteries that we have are wonderful and very good for mobile electronics and all the rest of it, but we try to go cheaper and better all the time.
Hmm.
And now that the market pressure is there, well, the research has happened, and the biggest companies in the world and some of the countries are seeing this as of sovereign importance, of national importance, almost it's almost like a military arms race, but it's a technology
Oh,
arms
yeah.
race in a way. Who has the best batteries? Because that'll dominate a whole range of different economic activities around the
Hmm.
world, whether it's cars, whether it's the electricity network, computers, the whole thing.
Hmm.
So it's so important that now billions and billions and billions are poured into it. And really, although lithium sulfur is more complicated and difficult than some
Yeah.
of the other technologies, it is one of the key ones that will deliver much better performance.
Yeah, so they say, Thomas, electric vehicle is basically a vehicle, is basically a battery on wheels, they say.
Yes.
So if you have a superior battery technology, would you forward integrate? I mean, couldn't you go into electric vehicle protection?
Oh
Um,
yeah, absolutely.
yeah.
Yeah. So as I said, Stellantis, which is the combination of Fiat, Chrysler, a few more. I think Peugeot and Citroën, whatever, they're in there. So it's a conglomerate. They are pushing hard for that, and basically all the large car companies are pushing hard because it
Hmm.
is at the moment the clearest form to get the lightest possible battery, and weight
Yeah.
is very, very important in cars. So I expect that to appear in cars, but initially it'll appear in something that's even more sensitive to weight. and that is anything that's up in the air. So drones are a clear target. And you think, well, drones, is that just for, hobby photographers and kids playing? Well, a big thing is happening now is a revolution in agriculture, where there is a need of what's called dawn to dusk surveying of the fields in terms of where the pesticides need to go, what the health of the plants is, where the water needs to go, where the fertilizer needs to go. And by mechanizing that with vehicles that are guided by that drone information, one is able to reduce costs dramatically. You reduce fertilizer costs by 70–80%, equally pesticide costs. So the load on the environment is a lot lower. The cost to the farmer is a lot lower, and that is enabled by the information that is possible to be gotten from drones, and then fed back to these automated machines that do the pesticide, the fertilization, and the irrigation.
Yeah, so we want to talk a little bit about that. So before we get into the agriculture part of it, so plastics. Plastics is something that you had a lot of work in.
Yeah.
And they say that the oceans have more plastic than fish anymore, which is a scary thought.
Yeah. So the work, I think, by the MacArthur Foundation is predicting that if we don't change anything, by 2050, there was by weight more plastic than fish in the oceans. Some people say it might be a bit earlier. So that's intolerable, right? That cannot happen. And that only represents 1.2% of the world's plastic that is made per year ends up in the ocean, right? So we're making a lot of plastic, and there's a lot of waste. Now, the big issue is, of course, we can recycle plastic simply if we have a a soda bottle, a milk bottle. They are already recycled to a very high degree. I think in Australia, the milk bottles are something like 80% recycled plastic.
Yeah.
Because they're easy to separate. The problem is when you have a chips packet, a Kit Kat packet, when there's a meat tray with film and a label and a tray underneath, or some packaging material, all of those things, difficult to recycle, and you can't put them easily in your recycling bin. We can take all of that plastic. We can take the easy to recycle, obviously, but also the difficult to recycle, and we don't want to interfere with what's already working. So we can take 80% of what's out there and make it into an oil, and that oil can be separated into 4 streams, which can go directly into the petrochemical industry. And the streams are naphtha, light cycle oil, industrial waxes, and bitumen. And we are the only technology in the world that can do it, because we can deal with when you have a label on a chips packet, it's not very colorful. It has a glossy backing, which is a very thin film of aluminium, and it's all on plastic. How do you deal with that? Well, we can. So we make the metals into a very fine metal oxide that we separate in the process, and we get rid of all the color elements of the dyes, and take the carbon elements and put them into the oil, all in one step. And we use compressed hot water to do that.
Yeah, so when I was reading through some of your materials, Thomas, I couldn't help thinking that Australia is so far ahead of EU and the US on this dimension. And these are universal technologies. And so how do we take this out of Australia and help the world? I mean, what are your plans to do?
Yeah. So what we've done is, well, first of all, what I just said, one can see as third party verified by the European Union. They evaluated a whole different raft of technologies, and we come out on top by 50% better than the next best in terms of environmental impact and footprint and water use and carbon footprint and everything. So that's sort of real, what I'm saying, which I think is important, because people say all sorts of things. So you can look it up. But our approach always has been that this is a global problem. And my personal people say to me, so what do you want to have achieved when you retire? And I said, well, I want to be able to take my finger out into the air, out of the window, and say, because of me, there are two part per million less CO2 in the air everywhere around the globe. That's my ambition. Now, it's maybe a bit crazy, but that's what drives me to make that impact. So we've been thinking about a global dimension from the beginning. So we have currently the world's largest commercial plant just being commissioned in British Columbia in Canada in collaboration with Canfor, the world's third largest forestry company. And we're integrating this plant to make biomass into sustainable aviation fuel with a variation of the plastics technology. So biomass into aviation fuel in a pulp and paper mill that's 6 million tons of sustainably harvested wood. And there's a fair bit of waste, and that waste normally is burned for process heat. But if you burn wet wood, it's smoky. You're using most of the energy just to evaporate the water. But we are using compressed hot water, so it's steam that is so compressed that it becomes a fourth dimension of water. It's called supercritical, and that is able to dissolve oil, but not salt. So it's really different. And so we are able to process that waste and to make sustainable aviation fuels. And then we partnered on the plastics because it's so big with another company in the UK to form yet another joint venture to take it out over there. And that joint venture sold a license to a US engineering company called KBR, one of the biggest engineering companies in the world. And they are rolling it out throughout their network of companies. So these plants are being built now in South Korea, in Japan, in Germany, in the UK, in the US, in Canada, and in Australia.
It's about biomass a little bit. So I don't know much about this, Thomas. I'm just so it took a little bit of a flat, I don't know if the right term, wooden pellets and stuff like that, right?
So we can we can take any biomass. So we have shown, we have a demonstration plant, 6,000 tons a year in Sydney in Australia. So we have shown we can take anything. So we can take bark, leaves, rice husks, corn stover.
Basically waste material.
Anything waste biomass. We can take sawdust, bits of leftover material from wood. So it doesn't have to be beautiful, clean, wooden pellets. We can take anything, all the leftover stuff. And that's really our credo. We don't want the world to make new biomass for us. We want to interact with what's already there and which has already been pre-aggregated, and it's sitting somewhere, and in a sense is a problem waiting to be solved, or it's just an opportunity for a much higher value use. That's what we want to do. So we don't want to replace, food for fuel. I think that's a toxic idea. So, for example, when you go to a sugar mill, there's a lot of bagasse. So the sugar cane that's been squeezed out, that often is just burnt, again, very inefficiently. And we can take that and make sustainable aviation fuel, for example. And there are quite large operations already around the world. So we just interface with that.
So your sort of focus is biofuel. So
that's right.
Sort of biofuel from waste, basically.
That's right. Yeah. And the reason for that is, if I go for chemicals, which is more attractive because you keep the carbon inside the supply chain and you don't burn it, there are two issues. One, the aircraft industry right now, they don't have a solution other than liquid organic fuels for quite some time. And if we want to have an impact by 2050, we need to use the technologies that are right out there now. We might have a hydrogen-powered plant by 2045, but it's too late. We need to do it now. And so therefore, it's a really good solution fit. But the other element is, if I start to do chemicals from this waste, what I make is a mixture of chemicals. And the cost in chemicals largely is their separation.
Mm.
And if I have a complex mixture to separate, and I don't yet have a business that is helping me to pay for the equipment that I need, at
Mm.
scale to make the separation economic, it's very difficult to finance. So just like the petrochemical industry, when they started 150 years ago, they were focusing just on fuel to start off with, and then dialed in chemicals over time. Every time there was an opportunity to make a bit more money out of the raw material, they would take some and make some chemical conversion there as well. And then over 150 years, we now have an extremely sophisticated industry that scrapes every little bit of value out of that barrel of oil. And
Yeah.
in the biomass, we are just basically like the petrochemical industry was 150 years ago. So we're just starting, and the starting point is fuel, because that's a mixture of materials, and all I have to worry about is the performance of that mixture. And
Mm.
there are standards that it needs to fulfill. So things like flash point, density, when it becomes a solid, when it starts to evaporate, the amount of energy per volume, per weight, the how quick it flows, and
Mm.
that's all very well defined. And if you hit all of those parameters, and they're about 25,
Mm.
then you have a product. And that's easier, believe it or not, than having a clean, clear chemicals from the beginning.
Yeah. So I'm thinking a little bit about policy, Thomas. So what you're doing is really fantastic.
Thank
It
you.
has huge societal benefits. Um, how should the governments think about what you're doing, right? I mean, Australia is a very advanced country, unlike the US. Um, so it's I don't know how the Australian government is thinking about this.
Yeah,
In the
so
US,
so
I think we are so far behind. Yeah.
well, we had a government, a series of governments which were not too keen on green technology, which is one of the reasons we had to go outside to do a number of things after demonstrating everything in Australia. But now we have a new government since a few years, which that is much more interested and in dealing with facts. And I think you have that problem in the US from time to time,
Yes.
that there are alternative facts, which is a theory
Alternative facts. Yeah, for
coming
sure. Yeah.
coming out of the US. Yes, so they were a little bit infected by that, but I think we are now back with the adults, and decisions are made, to a significant degree based on the physical reality
Mm.
of the world, and then there's a political interpretation of that.
Mm.
So what do we need to do? At the end of the day, CO2 emissions, climate change induced, CO2. It's a really big problem. So the policy settings need to be so that is reduced, that the CO2 emission is reduced in some manner. So is the government the best suited to be a technology picker? I don't think so. That'll just end up, which company has the best lobbyists, what previous relationships are there. I think the
Mm.
market will settle that. But I think what's really important is for the governments to set expectations in terms of cost of maybe a ton of CO2. That will be really helpful,
Mm.
because then I can calculate it, right? If there's a carbon tax, or if there is some carbon trading scheme that's verifiable and that is well designed and enforced by the government.
Mm.
Equally, carbon import tariffs, right? So you have a country that is doing very dirty things in their manufacturing, and therefore is able to undercut people who are producing with a much higher environmental credential.
Mm.
That's not fair. So one can adjust import tariffs, for example, based on that. There's obviously, space for abuse of that as well. There's no perfect system, but
Yeah.
I think regulation is where the government can step in, and through regulation, one can generate market incentives
Yeah.
for companies to say, well, if I do this, I have a higher profitability.
Mm.
But the safety in terms of the predictability of the regulatory environment is really important. So if
Yeah.
you have higher up politicians saying, if we go in, we will abandon everything, Well, that is not a great signal to invest in technology, which is going to last at least 10, 20, 30 years, right, in terms of investment payback. So that has been a big issue in Australia, and I think it's a big issue in the US, because your investment, was it your Inflation Reduction Act, if Trump gets in, I think is potentially going to be repealed to some degree. So that is generating uncertainty. And if there's a lot of uncertainty, it's difficult for people to put in hundreds of millions or billions in investment. So that's the role of government, to provide certainty and to provide a regulatory environment that is focused on reducing CO2 emissions.
Yeah, I mean, you're a poster child for this, Thomas. So, University of Sydney, you teach there. You're teaching the next generation, but you're also doing commercial stuff, and I think that is where it's going to be. I mean, it's you need academic input, you need commercial input. I don't know. I mean, I don't know of too many universities in the US doing stuff like that. I mean, I don't know. I mean, I haven't really looked into it, but I'm just speculating. Yeah.
Yeah. So I mean, there's a healthy. So yeah, if I take Berkeley for example, or MIT, there are quite a few professors with their startups. So the US is doing well. The risk or the tolerance for risk in the capital markets in the US is higher than just about anywhere else in the world. In the free markets, I mean, for a state-run economy is different because there can be a program and people say this is what you can do, and somebody made that decision. But for a free market approach, the tolerance for risk is biggest in the US, and I think you can be very proud of that. And the outcome of that, of course, is clearly to be seen. You know, some of the biggest companies in the world, technology companies, they're all from the US, because people have been able to go big and go early. And when there were failures, it was just part of the race to become the best. And
Yeah,
that mentality is
yeah.
not so much European and Australian, and that's something that we sometimes look somewhat enviously across the ocean.
Yeah, so I want to get your perspective on this. So I think we have to go also, but sort of the academic commercial collaboration, because these are emerging technologies that still needs research, still needs a lot of ideas to come through. I haven't really seen that much in the energy arena in the US. I don't know what your perspective is.
Yeah, it's a really hard game, and you've got to be a bit crazy. So that might be, the reason. So for me, that I'm a bit crazy, and I've done 4 successful startups that are all global. So maybe somebody has the gene sometimes. But it is most academics, when they, because I'm asked by Sydney University to help other academics to also make the jump. But most academics, by character and nature, when they see what's involved, become less enthusiastic to really be there
Yeah,
all the way at the forefront with the personal exposure. The financial risk if you're a director. I mean, you're personally liable.
it's huge.
Your
Yeah.
house can be taken away, so that is all a bit scary, and I think that's certainly a hurdle. But there are quite a few, especially in the biotech area, people at Scripps, professors who come with their own helicopter now to work. I mean, there are some quite successful people out there.
Excellent. Yeah, this is great, Thomas. I know that we didn't get into all your technical papers. I can understand that. But I
That's all
think
right.
I learned a lot from it. So yeah, thanks so much for spending time with me.
Okay. Well, thank you very much for the invitation and the opportunity.
Thank you.
Thank you. Bye bye.